Bismillahirrahmanirrahim. Assalamualaikum and good afternoon and good morning, everyone. Can you hear me?
Yes, doctor.
Okay. Today is a class, replacement class of face-to-face. So if you feel you have something to do, you can go because all are recorded. Okay, and you can listen to it later. So we continue to the slide number 84, guys. Okay. Improving the transient response using a PD controller, proportional derivative controller. We are looking at example 5. Okay. So for a unity feedback system with an open loop transfer function, 50 over S plus 50 is given, where this is a second order system. And the system type is 1. Okay. So determine the overshoot percentage and settling time of the system. And then you have to design a controller to have a 50% reduction in the OS and 4-fold improvement in the settling time. Meaning that the OS new is 1/2 the previous OS, and the new settling time is 1/4 compared to the old settling time. So since this is the closed loop, this is the open loop transfer function. So we derive the closed loop as usual, and then we get the 50 over S square 5S plus 50, which can be written as S square plus 5S plus 50. Okay, so you are required to find the overshoot percentage and settling time. So in order to find the overshoot and settling time, you have to use the compare with the standard second order equation, which is written there, okay, which is omega n square over plus omega n square. Okay, then you compare left and right. Okay, so from there you can get omega n square 50. Omega n is square root 50. Okay, which is you look here, square root 50 7.07. And then find the zeta, which is 2 zeta omega ns plus 5s. You compare, and then you will get the zeta value, which is 5 over 2 multiplied by omega n 7.07, which will give you 0.354. Okay. So we got the two values here, which is important to get the overshoot. So we compare. So from there, from the zeta omega n, you can what do you call that? Use a graph. Okay, the standard graph. Remember this graph? Okay. So 0.354, let's say here. 0.354. Which is correspond to the overshoot percentage. Okay, so if you use the graph, it is about 30%. Okay, 30.5%. So you get the overshoot percentage with the correspondent zeta. No need to use formula because it will take time, okay, and consume a lot of time. Then after that, you calculate the, what do you call that, the settling time, ES, okay. So how to calculate the settling time is from the denominator closed loop transfer function, which is s squared plus 5s plus 50. Am I right? Hello? Hello? Then you find the roots. What is the roots? Here, help me. Help me.
It's 2.5 plus 6.6.
Can't hear you. Which is minus 2.5 plus minus j
6.6.
Okay. So from here we can what do you call that? Construct the polynomial by s plus 2.5 plus j 6.6 can s plus 2.5 minus j 6.6 equal to 0. Okay. But the important thing is you want to have the roots. Okay, the roots is minus 2.5 plus minus j 6.6. Okay, which is equal to minus zeta omega n plus minus j omega d. Where this part is real and this part is imaginary. Right? Okay, so far okay. So the settling time is 4 divided by real, am I right? So 4 divided by 2.5, which is equal to 1.6 second. And the peak time is pi divided by imaginary, okay, which is equal to pi 6.6 equal to 0.476, 0.476 second, okay? So our concern is the settling time is 1/4 TS. Am I right? Okay. 1/4 this one. Fourfold improvement in the settling time. Improvement meaning shorter lah. Shorter 4 times. Okay, compared to the old one. So 1/4, 1.6 second. Am I right? TS new. So 0.4 second. Our target, our spec design. Okay. And then the what do you call the new overshoot? Oh, sorry. The new overshoot is 50%, yeah. 50% of the existing overshoot. So 50% actually is half multiplied by the existing overshoot. What is the existing overshoot, guys? The one that we get from the graph. There, here, all right. Hello, 30.45, 30.45 percentage. So how much? Roughly about 30.45 divided by 2. 15.22, eh? Hello? You sleep, huh?
Yes.
Just to sleep. Too many sleep already. 7 days sleep already. Okay. Okay. So what next is to find the new dominant pole. Okay. To find the new dominant pole. So we already get there here. Okay. So the desired closed loop poles will be what? Will be what? Will be what? Will be what, guys? How to find the desired overshoot? We already have desired settling time. So desired overshoot is there. So we have to find the desired closed loop poles based on the new 15% there. Okay, so we just put it here. Desired settling time is already 0.4 seconds. Am I right? Desired overshoot is 15.22 kan? So how to find the desired poles or dominant poles? So you just use here TS new kan? TS new is equal to 0.4 second is equal to 4 divided by real new. Am I right? Hello? This one is new one. Okay. So the real new is 4 divided by 0.4 second. How much? 4 divided by 0.4 second. 10, 10. Right. So this one is a real new. Then the real imaginary. Real imaginary. How to find the real imaginary? because this one, you have to look the graph. Okay, zeta overshoot percentage. So 15.23. 15.23. So you will get the new zeta. Okay. Can you check what is the value of zeta? There you go. Okay. This one is 10. The imaginary is omega 1 minus zeta square. So you have to calculate the omega n values. How you calculate the omega n values? Okay, so if you follow this one is a fourfold improvement. So you calculate the new omega n here. Okay, the new omega n here is 19.49. Okay, so you insert inside here. So you get minus 10. Then imaginary, you insert inside here 19.49 with the zeta value 0.513. Then the square root, then you get 16.73. So this is the new closed loop pulse. Okay, desired closed loop pulse is minus 10 plus J 16.73. Okay. So therefore, this one will be the test point. Okay. Will be the test point here. Okay. Where the open loop pulse 0 is the angle of theta 1. Open loops minus 5 is angle theta 2. Then we locate the new zeros here, and the angle correspondent for the new zeros is theta 3. Okay, so with the using the trigonometry, okay, so theta 1 and theta 2 is total of angle due to poles minus total of angle due to zeros equal to 180 degrees. So theta 1, okay, you get from alpha 1. Okay, this is alpha 1. Theta 2, you get from alpha 2. This is alpha 2. Okay, so theta 1 is 120.87. Theta 2 is 106.64. And then therefore you get theta 3, 47.51. And then for the theta 3, okay, is a triangle where the height is 16.73. The imaginary new part, the new imaginary part, and the distance from the zeros to minus 10 is x. So find x, 15.32. So therefore your new z is minus 10 minus 15.32. So you get minus 25.32. That is your new zeros, which is located here. Okay, and then find the gain. Okay, find the gain values. This one is using trigonometry, so the other solution is by using the this one. So now the GPD and G is equal to S plus how much tadi? S plus 25. Sorry. S plus 25. Yeah. 25.32. 25.32 kan. So you nak calculate dia punya gain berapa? Gain dia berapa? Then again here, the gain is 15. So how you get 15? Okay, you get 15 from the calculations of the here. K is equal to S plus 5 and S plus 25.32. Okay, so you replace this with the dominant pole, which is there. Minus 10 plus J 16.73. 16.73. So insert inside here. So you will get the values is 15. Okay, 15. So this is the new gain. So therefore the GPD is 15 S plus 25.73. Okay, 25 plus 32, sorry. 25 plus 32. Okay, which is what is the standard for the, yeah, okay, KD S plus KP KD. KD S plus KP KD. Okay, double confirm. Okay, so KD is the derivative gain. KP is the proportional gain. Then you compare. Okay, so you compare KD is equal to 15. KP over KD is equal to 25.32. So therefore KP is equal to 0.3. 0.3. Okay. But we have to multiply with the origin. Okay. The origin gain from the transfer function, which is here. The given here. This is the original gain. Okay, so multiply it with the 0.3, then you will get KD is equal to 15. Okay, K equal to 15, then KD is equal to 0.3. And this is your final overall transfer function. So when we redraw, due to the zeros, so the root locus become circle. And when we draw the line for the zeta 0.514, it will cross twice, okay, at 59.13 degrees. But the bottom line is our target is to make the settling times improve by 4 times or shorter by 4 times. So this is before PD controller. The settling time is 1.55 seconds. And then after PD controller is 0.385. Okay, so we calculate the ratio 1.55 divided by 0.385. What is the ratio that you get? 1.55, 0.385. Okay, so roughly you will get 4. So it fulfill our target designs. Okay, the ratio is 4.0 to 6. So we assume it as 4. So you make sure that our target for design, first thing is system is stable. Second thing is fast response. And number 3 is the 0 steady state error. So this is our target. Okay, in any controller design, either PI, PD, or PID, you have to make sure that it fulfill these 3 targets. So we go to the PID controller, guys. So PID controller is the combination of the proportional, integral, and derivative controller. Where in hardware, you have some sort of this module, hardware module, where the industrial buy and connected, cascaded to the model, okay, the input model. This one consume a lot of money, okay? So if you don't have money, you buy the cheapest one that is using the Arduino Uno, okay? To control the proportional gain, integral gain, and derivative gain, okay? Basically, it fulfill the block diagram of the PID controller as shown here. So when you show this block diagram, proportional, integral, and derivative in parallel connections, meaning that it is a PID control, and the function of PID control is to improve the transient response and to improve the steady state error, or to make the response fast and to make the steady state error 0 simultaneously. Simultaneously serentak, 2 in 1 together, okay? So that you can achieve the stability, fast response, and new 0 steady state error. So that's why this is the, what do you call that, in general, PID
الو
controller.
داريوس الجزء طلعت ولا لا؟
Hello, Baka?
يرسل في الجروب.
Okay. So PID controller is a combination of PI and PD. Okay, first we design the PD for transient response, then we design the PI to make the steady state error 0. And this is the transfer function of the PID controller, Kp proportional plus Ki over S integral plus Kds the derivatives. Okay, so when we simplify and derive, so it will become the standard second order, standard PID, which is Kd at the outside, derivative controller, gain multiplied by S square plus ratio Kp over Kd multiplied by S plus Ki over Kd ratio. Then we will get the S plus Z1 over S and S plus Z2. So Z2 is the difficult one. You have to calculate, okay, according the rules to find the new zeros. But Z1 is quite easy. You just put the 0.01. So the PI controller completely solved, okay? The challenge is at the Z2, okay? So to implement it for PID controller, consists of 2 zeros and a single pole at the origin, okay? That is the approach, okay? So we look into this problem where you have a system where the open loop transfer function is K, S plus 8, S plus 3, S plus 6, S plus 10. Okay. S3610. 3, 6, 10. And minus it. Zeros. Okay. So what do you expect from this plot is a transfer function. Let's see. There you go. Okay. Because of the zeros, so there is no cross at the origin and the imaginary axis. Okay. So this is the plot, okay, where you have -3 here, -6, -8, and -10. Okay. This is the open loop, and this is the closed loop. And the bottom line here is the characteristic equation. Okay. So our spec design is spec design. Number 1. What is the spec design number 1? Lim? Lim Yuan King?
8 times 2/3 of uncompensated system.
Tak dengar Lim. Can't hear you. Microphone. TP Neo. 2/3. Lim? Correct.
Yes, yes.
Betul? Lee? Number 2, Lee?
20% overshoot. Overshoot percentage of overshoot equals to 20.
20%. Overshoot. Overshoot, eh? So this one will go to zeta. And then spec number 3. Or 0 steady state. Okay. 0 steady state error. Okay. Spec design, or we call it as a target lah. So far, okay? Okay. So 20% overshoot. Again, we use the graph. Okay. %20. So what is the value of zeta over there? .456. Okay. So if you don't want to use the graph, you can use the formula. Okay, but this one consume a lot of times. So you use this one, 20%. So, okay. So you plot the, what do you call that? Use the protector and draw the zeta line. So zeta line is cos theta equal to zeta. So cos theta equal to 0.456. Theta is equal to inverse cos 0.456. Abu Bakar Halim. What is theta, Abu Bakar?
Yeah, yes, doctor.
Theta. Inverse cos 0.456. $62.87. Okay. 62.87. Then you find the dominant pole. Okay. So how to find the K value over there? How you get gain 1, 2, 2? From the computer, you get 1 to 2. But by calculations, Amiro, Cordoso, ada. Nevin, how you get K? Idu. Said Muhammad,
Yes, Doctor.
how you find K?
By using the dominance rule.
Okay, good. 10.6. Okay. So you insert inside here. So you will get 1, 2, 2. Okay. Right. So this is the dominant pole. Okay. Then the peak time is pi divided by imaginary, which is this one. So 0.296. This is the old one. But the new spec is TP new 2/3 multiplied by TP. Okay. So this TP will goes here, then you get the new one. Okay. Then calculate the new omega n. Okay. So the new omega n is by using this formula. This is actually pi divided by omega d. Okay. So omega d is equal to omega n square root 1 minus zeta square. So you will get the new omega n at 18.58 radian per second. Then from there, you will get the real closed loop pulse, the new one, minus 8.47. And then the new imaginary, which is J16.54 by using the new omega n and the zeta, okay, 0.456. Zeta no change at 20%. Okay, maintained at 20%. And this is the new closed loop pulse, which is minus 8.47 plus J16.54. When put it in the graph, sketch graph, okay. And from there, you calculate the theta 1 for pulse at -3, theta 2, pulse at -6, theta 3, pulse at -10, theta 4, pulse at -8, and theta 5. The unknown zeros, okay, for the PD controller. Then use the angle criteria, theta 1, theta 2, theta 3 summations. That is the total of the angles due to the poles, and theta 4 plus theta 5 is the total of the angle due to the zeros. Okay. Then theta 5 is 19.88 degrees, which is the angle due to the new zeros. Construct the triangle or the theta phi and then calculate the angle. So you will get 45.74. So then you add, you get minus 54.21, which is here. Okay, on far left. of the S-plane. Then calculate the gain. Okay, this is using a triangular, but the best thing is you just use the easy one, the one that I teach you, which is S plus 3, S plus 6, S plus 10, magnitude, over S plus 8, S plus 54.2. Okay. Then you use this value, insert inside here. And you get the value, the gain is 6. Okay. So I hope everybody knows how to do this using your calculator. Okay, so this is the calculation to get the new zeros for the PD controller, the new desired closed loop poles, and the new peak time. Okay. Then the last step is PI controller. Just add 0.5 because 0.5 is very near to 0 origin and it can cancel each other, but at the same time, it increases the system time. Okay. Then you will get the KP, KI, KD by comparisons. Okay, which is 4.6, 259, and 128 respectively. Okay, for the GPID controller. And this is the way you get the values 4.6, 2959, and 128 for the PID controller. So before PID controller design, the peak time was 0.298. Okay, before. After, peak time was 0.196. Okay, so we can see that the ratio 0.298 divided by 0.196, how much? The ratio 0.298 divided by 0.196.
1.5.
Again, 0.298 divided by 1.96. 1.5. So it's 2/3. Okay? It's 2/3, guys. Right. So when you plot together in the graph, so you will get PID is the best response compared to PD and compared to the uncompensated. Uncompensated give a high ESS. PD, small ESS. PID, zero ESS. Small. This one, 0. Okay. So that's why we learn PID in this subject. Ten minutes break. Okay, guys. 10 minutes break. Any question?
No, Doc.
Okay, 10 minutes break. 12 o'clock start. Okay, guys, we continue the second half of the lecture by referring to the slide 110, PID, controller tuning. So, as I mentioned before, in PID controller, we have to find the gain of KP, KI, and KD. But we do the calculations. We do the, we call that, find the zeta, find the dominant poles, find the new real, find the new omega n, find the new imaginary, and then we draw the new dominant poles, and then we estimate the value of zeros that fulfill our desire of the overshoot percentage, of the settling time, or of the new peak time. But in this method, you don't have to do that, okay? What we will do is we do the calculation or procedure that can give you the new KP, KI, KD without using all the calculation previously, okay? So this method, we call it easily adjusted, okay? Involve KP, KI, and KD, okay? It can be taken offline, okay? Calculated by offline, okay? Before we implement into the system. So this is some of the method that used in the PID controller tuning, okay? Manual tuning where no maths required. Okay, it required experienced personnel. So the guys just estimate the KP, KI, and KD based on experience. So we call it as a try and error method. The one that we are going to study and include in our subject is the Ziegler-Nichols method. Okay, so this method is a proven method, established method, and can be online implementation. Okay, but it will make process upset, some trial and error, and very aggressive tuning. Then the other one is using a software tool, so we call it as a PID tuner in the MATLAB. Okay, consistent tuning, online and offline measurements. Okay, and various technique can be implemented. It costs give you some costs or a training required to do the calculations. And the other one is a Cohen-Kuhn method for tuning. Is a good process model. Okay, something to do with the process model, single tank, double tank, or triple tank. Okay, and it has some mathematics implementation, implement offline, and good for first order process estimations. So the following table summarizes the effects when the parameters are tuned manually. So we have the three gate, KP, KI, and KD, where the rise times, when the KP decrease, the settling time will have a small change. Overshoot will increase, steady state error will decrease, and stability will be degrade. Degrade meaning no improvement, okay, and it is degrade until it's marginal, and then it will be unstable. For KI, we playing with AI, KI, so it will make the rise time decrease, it will make the settling time increase, overshoot increase, steady state is confirmed, eliminate or become zero, but the stability is degraded. But KD, when you have a rise time in minor change, you find the settling time decrease, overshoot decrease, steady state no effect actually in theory, and it improve if KD is very small. Okay. So the one that we are focusing now is the method which known as Ziegler-Nichols. Okay, when the system or the models cannot or difficult to be obtained, either in the form of differential equation or transfer function. So that's why we use the Ziegler-Nichols. It is an effective method for the parameter adjustment by using the method called ultimate cycle method. Ziegler-Nichols is using ultimate cycle method. And the procedure is shown here. The first one is, first you set the KD is equal to KI equal to 0. Okay. We set KD equal to KI equal to 0, which is to minimize the effect of derivation and integration. Okay. After that, the second method is you increase the gain Kp, okay, until the system reach the critical stable and oscillate. So when this happens, the closed loop poles are located at the imaginary axis. So you obtain the gain, okay, Ku, and the oscillation frequency in radian per second on that particular time. Number 3 is you calculate the gain Kp that is supposedly needed using a formula in the table. So for Ziegler-Nichols method, there is a table will be attached to the test and exams so that you can calculate the gain Kp. And then finally, based on the required type of controller, you calculate the necessary gain using the formulas in the table. So this is the table, okay? So you use the third one, the third row, where PID is equal to 0.6 KU. Then you find the TU, divide by 2, you get TI. Then TU divided by 8, you get TD, okay? So Kp is the proportional controller, which is 0.6 multiplied by Ku. And GPID is shown here. Okay, so this one is actually Ki is 1 over Ti. Okay, and Kd is equal to Td. Okay, Kd is equal to Td. Shown here. Okay, so this is the similarity between these transfer functions. Okay, we go for the examples using the ultimate cycle method. Okay, so design PID controller for a unity feedback system with the open loop system, which is given as this. Okay, 300K divided by S, SQ square plus 30S plus 100. So is a third order system with the type 1. Okay, system type 1. Right, so we plot the rule locus for this to see the flow of the signal. So we have 3 rule locus ended at infinity. Okay, so this one is 0, -5, and -25. Okay, and the time response with one controller, peak time 1.11 second, settling time 2.45 seconds, and of course the steady state error 0 because our system is type 1. Okay, then start with the procedure number 1, which is assume Ki, Kd equal to 0. Okay, right, we find the closed loop transfer function from the open loop. Okay, this is the open loop. So closed loop is G 1 plus G simplified. So you get this closed loop transfer function, and you find the characteristic equation. So this is the characteristic equations. Okay, inside the Roth-Lewis table. Okay, S cubic 30S square plus 100S plus 300 Kp. So this one is 1, 30, 100, 300 Kp. And the rest is 0, 0. Okay, continue the fill up. Okay, so I hope by this stage you know how to derive this. Okay, so the theory said that the first column, okay, of the row width is greater than 0, meaning that this one, first column is this one. Okay, so that is your first column. Must greater than 0. So 100 minus 10 kp greater than 0. Then minus 10 kp greater than minus 100. Simplify, kp is less than 10. 300 kp greater than 0, kp greater than 0. So that's why the range of stability for kp is between 0 and 1. Okay. So K critical, kp critical is when the system is marginal stable where equal to 10. Okay. So kp actually is equal to K critical is equal to Ku. Okay. The alternate cycle, which is equal to 10. Okay, so you use this value of K, you insert inside the even equation. Even equation 30x squared plus 300 kp, you get from the Rolf width over here, line s squared. Okay, insert the value of 10, then simplify and find omega. So omega is equal to 10 radian per second. Okay, 10 radian per second, guys. Okay, so this one, find the ultimate period TU. Okay, so TU actually come from omega 2 pi f equal to 10. So this one, omega, is 2 pi f. So f is equal to 1 over TU. Okay, so that's why you get 2 pi over TU. Then you rearrange the equation. TU is equal to 0.26283. Okay. And then you already find the TU. You already have KU. So now you can use it inside this formula. Okay, to find the KP, TI, and TD. So KP 0.6 KU. KU is 10. So KP is equal to 6. TI is equals to TU divided by 2. TU is 0.6283 divided by 2, 0.3141. That is for TU. TD is equal to TU over 8. So TU is 0.6283 divided by 8, 0.0785. So you already find KP, TI, and TD. So you insert inside here, KI is equal to KP divided by TI, which is 19.1, and KD is KP multiplied by TD, which is 0.47. So you insert inside, so you will get the, you can put inside here, KD, KP, KD, KI, KD. Then you will get the GPID transfer function. Okay. Right. The next one is the same examples as previous. Okay. Same examples where you are given a control system with a unity feedback as shown here. The third order, type 1. Okay, so design a PID controller using Ziegler-Nichols closed loop. Okay, same as previously, but assume Ki and Kd is equal to 0. Find the open loop transfer function. Find the closed loop transfer function. Okay. And this is your characteristic equation. Insert inside the Rolf width, okay, where 1, 4, 3, and Kp. Then beside is 0, 0, 0. Then fill up the column, the next column, which is row S1 and S0. So from here, 1 is greater than 0. Okay, 4 greater than 0. Then 12 minus Kp divided by 4 equal to 0, simplify. So Kp is equal to 12, equation 1. Then Kp greater than 0, equation 2. So the range of stability is between 0 and 12. From there, the critical is 12. When Kp is equal to 12, so Kp is equal to K critical equal to Ku, which is equal to 12. This is your even equation from the Rolf-Lewis. Okay. So you insert the K value 12 here. Simplify square root 3. So square root 3 is how much? .73. Okay. Then find the TU using this formula. Omega is equal to 2 pi f, or 2 pi divided by TU. 1.73. Okay. So which is 6.2, 3.26276. So you already find TU, you already find omega U. Okay. Sorry, KU, TU, then find the KD using the formula in the table. Okay. So Ki and KD is shown here, 4 and 3.26. And you already know Kp, so insert Kp here, inside Ki here, and inside KD here. So you will get the final transfer functions. Okay. So the second method, Cohen-Kuhn method, is an optional method. So this one you can read by yourself. Okay. Because it's not coming out for the exams. So I leave it to you for your own reading. Okay, not included in the final exams for the Cohen-Kuhn method. So we end our chapter 2. Okay, so I hope by this stage you know already how to design the P controller. Okay, PI controller, PD controller, PID controller, and the PID tuning method using Ziegler-Nichols method. Okay, so I think that's all, guys. So I see you in Friday, inshallah, 10 o'clock face to face. Any question, guys? Any question? Sharif? Okay, if there is no question, we end it here, and I see you on Friday. Assalamualaikum. Good afternoon. Bye-bye.
Okay, doctor.
Thank you, doctor.
Thank you, doctor.